Okay, so I'm going to try and kind of monitor my own time now. So we're going to move on to the last talk, which is me, and I'm going to talk about convergent evidence that demonstrates the suppressive effects of white noise masks. I'm probably going to move around a bit too. Okay, so as I mentioned in my introduction back at the beginning, noise masks raise detection thresholds, and the traditional explanation for this has always been that what the noise is doing is it's increasing the variance in the detecting channel. So in other words, your signal to noise ratio goes down because your noise is going up. But there's another possibility, and if we use broadband noise masks like white noise, then all of the power of the noise that falls outside the bandwidth of the detecting channel is going to activate lots of other detecting mechanisms, and they might have a suppressive effect on the detecting mechanism itself. So that means that your signal to noise ratio is going to go down because your signal is being actively suppressed. And we talked about some of the ramifications of this in a paper last year in Journal of Vision, so I'm not going to go into too much detail on all of that, but what I'm going to talk about today are two slightly more direct ways of assessing the suppressive effects of broadband white noise masks. So the first thing uses a very cool technique which is kind of new to me. So this is called steady-state EEG. Basically in steady-state EEG, you measure the electroencephalogram, usually at occipital electrodes if you're interested in vision, and you measure the response to a flickering stimulus. And what you're then able to do is pick out the amplitude of the neural response to that stimulus from the Fourier transform of the EEG signal. So you take the Fourier transform and you look precisely at your stimulus frequencies, which tend to be somewhere around here, sort of 5 to 10 hertz, something like that. And as you parametrically vary things like contrast, you're able to measure contrast response functions. Here is a figure from a paper from last year from Journal of Neuroscience by Shai-Wei and Norcia, and this was really the one that got me very excited about this whole technique, because what they do is they measure contrast response functions using steady-state EEG in the presence of different sorts of masks. So they get a rightward shift, these contrast gain control effects, and they're able to measure that directly at the scalp in human observers. So I thought it would be great to compare the effects of different types of masks using this paradigm. So I set up an experiment where we had various sorts of stimuli. What I actually do is arrange, I tile my stimuli in an 8x8 grids just to give me a very strong signal, and what we get is, so we have a look away for epileptic, I said that too late. We have a flickering grating, that's just our basic target, and we can add things like an orthogonal mask, flickering at a slightly different frequency, and we can add a noise mask as well. And a few little methodological things, because we put stimuli on for a long period of time, about 10 seconds or so at a time, trial by trial, we randomise the orientation of all our stimuli just to avoid any local adaptation type effects. Okay, so here's some data. These are averaged across 6 observers, and first of all, just to give us a baseline, with no stimulus, not much is happening. Actually, you do get a baseline sort of noise level from EEG, but I've subtracted that out, so everything is just going to be relative to this 0 baseline where there's no stimulus being displayed. As we increase the target contrast going on the x-axis, we get a very nice contrast response function. So this here is just the Fourier amplitude at the target flicker frequency coming straight out of the Fourier transform of the EEG signal. So that's exactly what we'd expect to see. It's very, very nice. When we add an orthogonal mask to our target, so it's a fixed contrast orthogonal mask, we see a very kind of straightforward gain control type effect. So we see a rightward shift in the contrast response function, and this is very similar to the sorts of things neurophysiologists have been reporting for about 20 years or so, so these classic contrast gain control effects. I also tried using my zero-dimensional noise. Okay, so this is the thing that Stan, if you were here for his talk, said he originally thought was silly. What you do is you just jitter the target contrast. Okay, and what that does is basically nothing really. So we don't see this gain control effect when we have this zero-dimensional noise, and that's exactly what we'd expect, because all you're doing is you're just slightly changing the target contrast trial by trial. We do have a small increase down here, but that's just because the EEG response is phase invariant, and sometimes at low signal levels, the noise will invert the phase of the stimulus. So that's kind of not very exciting. The main point to take away here is that the zero-dimensional noise doesn't give us any contrast gain control effects, and that's exactly what we would have hoped. What about two-dimensional noise then? we have white noise, broad bands, two-dimensional white noise. We can see in the yellow function here, that has a very, very similar effect to the orthogonal mask. So it's having a suppressive gain control effect, and we can see that directly in the contrast response function coming straight out of the back of somebody's head. We can also have a look at what happens at the mask frequency. This is 7 Hz from my experiments. You can see as you increase the target contrast, the response to the mask goes down, and that's just because this target is having a suppressive effect on the mask. So that's not terribly surprising. But the other nice thing that I thought we could have a look at is the variance. I'm not aware of anybody having looked at this before, but I don't know the steady-state literature particularly well. So here is just the signal variance when there's no target. So that's our kind of baseline. That's just the noisiness of the EEG signal or tool or something. Bit of a surprise when we look at the variance as we increase target contrast. Now, I come from a background of psychophysical models where we assume additive noise for the various reasons that Keith was just describing. But what I found when I looked at the variance of my EEG data is, in fact, that variance increases as a function of target contrast. So this is signal-dependent noise. This is multiplicative noise. And I was pretty surprised about this. I don't really have a very good explanation for why this should happen, but it's there in the data. And it turns out to be quite a useful tool. Because of this signal-dependent noise, when we add an orthogonal mask, which suppresses our target response, the variance actually goes down. So the orthogonal mask reduces the variance of the response to the signal. Our zero-dimensional noise increases the variance, and that's what we would expect of a noise mask, because what we're doing here is trial to trial, we're actually physically changing the target contrast, okay? So it'd be pretty weird if the variance didn't go up in this condition. But that's what we expect to see for a noise mask, because the whole point of noise masking is that it operates by increasing the variance within the detection channel. Okay, what about two-dimensional noise then? Well, we've already seen that two-dimensional noise has a suppressive effect, and so it's perhaps not that surprising that two-dimensional noise reduces the variance of the signal response because of this suppression. So we're reducing the response, and therefore we reduce the variance because the variance of the signal is response-dependent. But look, that's totally the opposite of what noise masks are supposed to do. The whole point of a noise mask is that it's meant to increase the variance within the detection channel. So the two-dimensional noise here, which is what everybody seems to use, or most people seem to use in noise masking experiments, is doing completely the opposite of what it's supposed to do. I find that very surprising, but very interesting. Okay, so we've seen some very clear evidence here that 2D noise can produce strong suppressive effects and that it doesn't increase signal variance. We can now ask another question about 2D noise, which is whether the suppression it causes is constant or if it depends on the properties of the mask, and specifically here, the temporal properties of the mask. So to look at this, I'm going to use a contrast matching paradigm. Tim Beath and I showed in our paper last year that perceived contrast is reduced by an added noise mask, so you get these suppressive effects. And if this is due to the same sort of suppression that we get from grating masks, then it should have similar characteristics to the masking that we get from orthogonal gratings. There's a really nice paper from Proceedings of the Royal Society in 2007 where Beath and Holmes show that as you increase the speed, basically the flicker rate, and decrease the spatial frequency of an orthogonal grating mask, you get more masking. So it's a very solid result that's been replicated a couple of times, which is just that suppression from orthogonal masks increases with stimulus speed. Now there are two ways to give noise masks a temporal component. The first way is to make the noise dynamic by bandpass filtering at a specific temporal frequency. So at the top there we have some 4 Hz dynamic noise, but the other thing you can do is just take a static sample of noise and counterphase flicker it, as in the bottom here. So I tried both versions of this, measuring perceived contrast for a 1 cycle degree grating embedded in noise. The grating, the standard always had a contrast of 21 decibels, and then we vary the target contrast according to a staircase. I also looked at what happens if you just have static stimuli, but you vary the presentation duration. So I'll show you the data of that first. Duration is just given along the top, and this is perceived contrast on the y-axis as a function of, well, here, duration. Anything below this dashed line indicates suppression being caused by the noise. So it's a non-veridical percept. What we see is, as we increase the presentation duration to the left-hand side of the plot, we get more and more suppression. That's kind of consistent with gain control effects building up over time. What happens if we vary the temporal properties of the mask, though? If we increase the temporal frequency, we tend to get more masking. So the suppression is strongest at temporal frequencies above about 8 Hz, and that's consistent with the Mies-and-Holmes finding with masking from gratings. If we use our counterphase flickering noise, we see a similar result. Over here we get high levels of contrast, perceived contrast reduction at the high temporal frequencies, though actually we see a slightly positive result down at lower temporal frequencies where actually we get a contrast enhancement effect. And I don't really have a very clear explanation for that, but it's been seen several times before in contrast matching using grating masks. So there are some Mies-and-Holmes papers from 10 years or so ago. Okay, so to summarise all of this then, we've seen that white noise can produce very similar suppressive effects to orthogonal gratings. So the suppression is shifting the contrast response functions rightwards, where we measure them directly using steady-state EEG, and it appears to be strongest at the high temporal frequencies, just like masking from orthogonal gratings. And it stands to reason, at least in my mind, that these sorts of suppressive effects could confound empirical estimates of internal noise that we get from using the noise masking paradigm with two-dimensional noise. And I find that rather troubling because there's, of course, a huge literature which has all kinds of interesting conclusions about how different perceptual deficits are related to the level of internal noise. So if our estimates of internal noise are suspicious, then so are all of those conclusions. Pretty much any of them could be exchanged for a difference in contrast gain control. Of course, there is a potential solution, which may or may not be silly, which is instead of using two-dimensional noise, to use dimensionless noise, so to jitter the dimension of interest. Now, in some situations, that's not really very controversial. So for orientation, it's pretty standard to just add an orientation jitter, as in some of the experiments that were described in earlier talks. But I think given that many people measure contrast detection thresholds, it's worth at least giving this technique a go and seeing where it leads us. Okay, so I just want to say thank you to some of the people that helped in this project, and also a huge thank you to all of the Symposium participants. It's been a very interesting session, and hopefully we're now going to have some very interesting questions. I think because we're running a bit behind time, I'm going to kind of roll in the questions to my talk into the kind of general questions to everybody, and I think we were going to set up maybe some chairs so we could get the speakers from the rest of the session to kind of come up and sit in a sort of talk show style panel, and perhaps we'll have some microphones and people can ask us difficult and probing questions while we sit in the line. But just while we're doing that, does anybody have any specific questions about what I've just been saying? Yes?
Yeah, thanks, Daniel. Could you say a little bit more about how you compute variance from the steady-state BP?
Okay, yeah, so what I do is I have multiple trials for each condition, and I calculate the mean for each trial from the Fourier spectrum, and then for each observer I've got 10 observations, I've got 10 trials, so I just calculate the variance within an observer, and then I average the mean variances across observers. There's probably another way of doing it, but that seems sensible to me, just because it wasn't, yeah, well that just seemed like